In this lesson, we continue our look at the mathematical relationships underlying radioactive decay. Here are the objectives. We saw in the previous lesson that if you have a number of radioactive parent nuclei, n, and you observe them over time as they decay, so time is on the x-axis here, you get an exponential curve in the number remaining. We also saw that if you define the activity as the decays per unit time, here, the rise over run of this graph, so the activity is the slope of this graph, then that's also lessening with an exponential pattern over time. In other words, if this axis were activity, clicks per second on the Geiger counter, we would also get an exponential curve, and we saw that they were vertical stretches of each other. We finally saw that the activity is related to the number of parent nuclei by the decay constant lambda, the decay constant being the probability that any individual nucleus is going to decay per unit time. Now, using calculus, we can take this part right here, and instead of delta n and delta t, we can make those deltas, the rise and the run, as small as possible, and we get dn dt. This is calculus notation, meaning that the rise and the run are very, very small. So in the limit, delta n over delta t becomes dn dt. The negative is still out front. And from this part of the equation, we still have lambda times n. Now, this is called a differential equation. It's an equation in calculus that has a derivative in it. And using calculus techniques that we won't go into, you can work out the first of these two equations. And that's that the number of parent nuclei remaining undecayed at any time, this is the number of parent nuclei, is equal to the number that you started off with, this is the initial number of parent nuclei, multiplied by the mathematical constant e, that's 2.71828, etc., to the power of negative the decay constant times the time elapsed. So we have four variables here: the number of nuclei at any given time t, the time t, the initial number of nuclei, and the decay constant. Be careful that e is not a variable, it's a constant. Again, remember that the activity is equal to the decay constant times the number of parent nuclei remaining, and so we can multiply both sides through here by lambda, and we get a new relationship for the activity. It looks the same, just replacing the n's with a's. So the activity at any time is equal to the initial activity multiplied by e to the negative lambda t. So we've got four variables here, and if we know any three of them, we can work out the fourth. So that's a powerful tool for problem solving. Now, this is stated in terms of the decay constant. What if we have the half-life, or what if we want to know the half-life? Well, there's an important relationship between the decay constant and the half-life, so let's explore that now. If we start from the equation above and we divide both sides by n sub 0, the initial number of parent nuclei, then this fraction is the fraction remaining of parent nuclei after time t relative to what you started off with. Now remember, by definition, the half-life is the amount of time it takes to reduce the number of parent nuclei by half, so this by definition after one half-life will be half. And similarly, that means that the time that we have up here is the half-life, and that's what we're going to solve for. After the half-life amount of time, you're going to have 1/2 the number of nuclei that you started off with. Now we have something that we want to solve for this exponent up here. So we use natural logarithms, take the natural logarithm of both sides, and because the natural logarithm is the inverse function of exponentiating e to the something, then we end up with just the exponent over here. And remember from your logarithm rules that this is 2 to the negative 1. We can kick down the negative, so ln 1/2 is equal to negative ln 2. And continuing algebraically, we can solve, and we get that the half-life is equal to ln 2 divided by lambda. The half-life is equal to ln 2 divided by the decay constant. Now, ln 2 is approximately equal to 0.693, and thinking of it that way might help you remember that even though there's letters here, it's not a variable. So this is a number divided by the decay constant. So a big decay constant, meaning a high probability per unit time that any nucleus will decay, results in a short half-life. And that's going to give you a high activity for a given number of nuclei. Now remember, it doesn't give you a high activity on its own. The activity is going to depend also on the number of nuclei. But for a given number of parent nuclei, a big decay constant or a short half-life is going to give you high activity. Similarly, a small probability per unit time of decay, a small decay constant, is going to give you a long half-life, and for a given number of parent nuclei will give you a relatively low activity. And because of this relationship between the half-life and the decay constant, when you have one, you can work out the other. And if you have the half-life, you can work out the decay constant that shows up here and here in these equations, and therefore use those equations. Let's finish up by talking about how to work out half-lives experimentally. Turns out that it makes a difference whether you're talking about nuclides with short or long half-lives. Let's start with short first. This is our equation, and so you can imagine that you could just take the time and the activity, so you wait for an amount of time and you measure the clicks on a Geiger counter, that's our activity, clicks per second, and you graph those against each other. Well, you don't actually quite graph those against each other, you have to subtract off the background count from this, like we talked about in the previous lesson. Once you do that, you have a graph that looks like this. This is my corrected activity minus the background count versus time. Now, instead of working out the half-life from this, which you could do, we're going to use the natural logarithms again to rearrange this equation and come up with another approach. If we take the natural logarithms of both sides, we get ln a is equal to, and using the rules of logarithms, we get ln of a sub 0 minus lambda t. Now, we can graph this as an equation. This is our y variable. This over here is our x variable. This is going to become a y-intercept, and this, so that's b, and this is our slope. In other words, if we graph ln a versus time, instead of graphing a versus time as we did down here, then we're going to get a straight line graph with a negative slope. And the y-intercept of that over here, the y-intercept is going to be ln a, and most importantly, the slope is going to give us the decay constant. The slope is equal to negative the decay constant. And because we saw that the half-life is equal to ln 2 over the decay constant, once we've got the decay constant, we plug it in there and we get the half-life. So that's what we do for short half-life nuclides. We just measure the activity as a function of time, and we can use this approach. For long half-life nuclides, that doesn't work very well because it's going to take too long for the activity to change. We'll just be waiting and waiting. Half-lives can be thousands and thousands of years. So what we're going to do instead is we're going to work out how many parent nuclei we have initially. We find the mass of the sample, and then we're going to need to know the percent purity, so we know how much is the actual parent nuclide of interest. We're going to need to know the molar mass. Using all of that, we can work out the number of moles, and then we multiply by Avogadro's constant to give us the number of actual nuclides. Once we have that, if we can gather all this information, then we measure the initial activity just off of the Geiger counter. And that's not going to change much because the nuclide has such a long half-life, so it's going to stay relatively constant over the time of our measurement. And now we just have a simple equation. We divide this number, a sub 0 by n sub 0, and we get the decay constant. Again, once we have the decay constant, we use that to get the half-life by the relationship that we saw above, that t1 half is equal to ln 2 divided by the decay constant. So that's a further look at the mathematical relationships underlying radioactive decay and how to find half-lives experimentally.